Okay, let's go ahead and start this presentation. This is Unit 1, all right, and this is basics. You guys have probably all seen this information before. It's not like it's new to you. If it is new to you, however, and you feel like you just didn't grasp it in class, let me know, okay? If you really are struggling with scientific notation, I'll put an example video up on YouTube. You can watch it as many times as you want to really feel like, until you really feel that you've grasped the concepts. There's a lot of great resources online. Sometimes it's not personalized to our class, so I like to do a lot of my own videos. So if you need something like that, especially around test time, let me know. However, if you contact me 10 o'clock the night before a test, I probably won't be able to help you. I'll probably be in bed sleeping, so just so you know. Unit 1 introduction, measurement. Okay, in order to make a measurement, we must first what? It's on your sheet. What's the first thing? You've got to know what you're trying to measure. Yeah. Okay. What's the second bullet point? Okay, now that seems pretty like straightforward, but it really is very important if you think about it. Okay, you must have a standard. Okay, so let's say that I wanted to measure the height of my classroom in farkles. Okay, we're not talking the dice game here. All right, what would that mean? What would that mean? You have no idea? You don't know what a farkle is? Come on, everyone knows what a farkle is. No one really knows what a farkle is. Okay. Farkles! It's not a unit we're familiar with. It's actually not a unit at all, okay? A lot of measurements were made up by the scientific community, defined by the scientific community. We could define a farkle as being the height of Mr. Bornheimer. So 2 farkles would be twice my height. We could do that, okay? We could make up our own units. But why is it not beneficial for us to do so? Say it louder. Other people would have no idea what we're talking about. Yeah, I think the Mackinac Bridge is like 30 and a quarter farkles. Yep. You know what I'm talking about? No, they'd look at you and they'd be like, you need help. Okay? And some people look at me that way anyway. So, farkles are not a unit we're familiar with. But what are some units we are familiar with here in the United States? Yeah. Meter. Well, sort of. Not so much so. What is another? Like a football field is how many yards? 100 yards. And if we count end zones? 120. Okay, yards. What is a yard broken down into? Feet. How many?
3.
Okay, and a foot's broken down into what?
12 inches.
12 inches. Yeah, see, these kinds of things, inches, feet, whatever, okay, it's really only unique to us. Americans like to feel special. Okay, we really do. We have this, I don't know what you would call it, this fascination with being unique or different. By the way, most of the world doesn't like to be different. That's why 99% of the countries use the same unit system, except us and 2 others. Okay, we decided to use our own standard of measurement. We don't even use the same current electricity systems as most other countries. Okay, we want to use American units. Metric is the standard. Okay, even in the United States, academic institutions and a lot of industry use metric. It's kind of interesting. About 10 years ago or less, the Michigan State of Michigan tried to switch over to metric. Okay, they couldn't do it because all of the contractors they work with work in American units. It would have cost billions of dollars to switch over all of the programs to different units, all of the diagrams, blueprints, everything. Okay, all of the road signs from miles per hour to kilometers per hour. Okay, so we stayed the same. It's a little bit of a hassle though. I used to have a van and it was only in kilometers per hour on the speedometer. Okay, so every time I was driving down the road, I had to convert, like on the spot. Like, oh, I'm going 90 kilometers per hour. Freak out the people in the back. They think I'm doing like 120, okay, when really I was only doing like 70 on the highway. So if you ever really want to, and that was my college vehicle. I had this big old red van. It was awesome. Okay, so we must have something by which to compare. We also have to have a tool. Okay, if I tried to measure the room with desks, this is probably not the best unit of measure because all desks are different. Okay, so we use specific tools. We use rulers, tape measures, thermometers, tools that have the sole function of measuring a specific thing. Okay, so these kinds of things are important in order to make accurate measurements, to test observations, and to go through the whole process of science. We have to have tools that are calibrated and that are standard in order so that our results can be interpreted by a general audience. Okay, so this seems like a very simple slide, but it really has important implications in everything that we do. All right, this is SI units. SI units are standard units. That does not stand for standard. It's actually a French word. Okay? If you're taking French, ask your French teacher, what does SI mean in SI units? Ask them, I don't know. I don't speak French. Okay? So, the French were really the first to adopt the standard unit system in 1795. It's been around a long time. Now you think about it. The United States has been around since 1776. Again, why did we not jump on that bandwagon? We like to be unique. Okay? They've had this unit system. It's been modified. It's still being modified. Okay? Our standards are changing. They're always changing. So they're not really all that standard. Okay? But whatever. The major benefit of a metric system, or SI units, and how we measure is that they're all related by powers of 10. Okay, so instead of saying 12 inches are in 1 foot, all right, we would, okay, say that there are 10 millimeters in a centimeter, 10 centimeters in a decameter, 10 decameters in a meter, okay, and then 10 to the third meters in a kilometer. All right, we have these great powers of 10. We can count up really fast. We can count down really fast. Okay, so being able to count by powers of 10 is really big because multiplying by 10 is one of the easiest things we do. You learn it in first and second grade. Think about if you could have mastered measuring in first and second grade, we wouldn't have to be talking about it now. But because we've learned feet and miles and inches and all of the other idiosyncrasies of American culture and measurement, we have to spend time now talking about it. Okay, so SI units. There are 7 base units. We cover most of them in this class. Okay, the first one's length, then time. Okay, what else do you think? Volume is one, sure. Temperature, yeah. Temperature is an interesting one. We'll talk about that. Okay, mass. Quantity is another one. And then candelas, or light. Candela literally means the brightness of a candle. It's kind of an interesting idea, right? Length, time, temperature, volume, mass, quantity. You'll notice that we actually mentioned one more than there are blanks. That's fine if you just want to write it in there. We use volume in this class. We don't use, however, moles really all that often in this class, which is really sad because moles are awesome. We're not talking about the little things in your yard that your parents try to kill, okay? You know, and however they might try to do that. But we are talking a unit of measurement, and we will discuss it briefly here this morning because it's so neat, I think. Okay, let's have a class discussion here real quick. How would you define a second? Don't look at your paper, just think about it for a moment. If you were a scientist and you were in charge of defining 1 second, how would you do it? Yeah. 1, 2. Okay, so like, yeah, you count, right? Does everyone count at the same rate? Okay, it's got to be specific, right down to a nanosecond. So like, I could say 1 1,000, 2 1,000, 3 1,000. That'd be about the same as what you did. But it's not exactly the same, and that's a problem for scientists. So what else could we use? Say what? A timer, sure, but how does a timer know how long a second is? Maybe. You're on the right track, sure.
Take the length of a day divided by a lot.
Okay, you take a length of a day, sure, but is every day the same length? No. Okay, so you're on the right track. Well, how else might we define a second? What do you think? How might we define a second? Bam! Yeah. Is that a second? Maybe. Does everyone's bam the same? No. Could you imagine everyone going around doing timing? Bam! 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 No, that would be weird, okay? Silly Americans. Okay? No, we have to have a standard. And you were right on track, okay? You were right on track. So here you go. It's a Slinky. I collect them. If you help out in class, you have really good insights, you may get something from me. All right, so yeah, we have to use physical phenomena. It was originally defined as a partial length of a day, okay? Time. It's actually now defined as, and I know we're all going to get this, It's been redefined as the duration of 9,192,631,770 periods of the radiation corresponding to the transition between two hyperfine level of the fundamental state of the atom of cesium-133 isotope. Whew, I know exactly what that is. Yeah, I absolutely do. Now, whether you do, you're probably thinking, whoa, what is that? Okay? You see, when you have something that's radioactive, it gives off radiation in definitive time intervals. We can calculate it mathematically, which is where math is so beautiful when it comes to radiation. We're not talking about like glowing people. But radiation is given off. Radiation is literally a physical particle. You can be alpha, beta. Gamma is not a physical particle. But there are different radiations, and they're given off at the same interval, very, very fast, but it's the same every time. So we counted this many intervals, and we said, hey, that's 1 second. It's the same for cesium. It's the same for the cesium-133 isotope everywhere. So you find this isotope and you count that many releases of radiation, and that's 1 second. And that's how we know what a second is. That's how it's defined. We can measure that using instruments, and when we measure that, we define that as 1 second. We have to define our units using physical phenomena. Okay, now it was originally defined as 1/86,400th of a day, but they found that days change. Okay, the Earth doesn't always spin exactly the same, believe it or not. Okay, so we had to change it. Okay, length. Length was originally defined as 1/10,000,000th the distance between the North Pole and Paris, France. Guess what? That's not that great, because is it really easy to calculate the distance between the North Pole and Paris, France? Did you take a ruler and go to the North Pole, and then you have your friend go to the Paris, France, and you stretched it all the way across? No? Why not? Oh, geez, oh, Pete. That wouldn't be very realistic. What might get in the way? Yeah, polar bears. Absolutely. I mean, yeah, lots of them. Terrible, dangerous. Yeah. Okay, well, it might take a long time, sure. Resources, water's a problem. How about mountains, valleys, people, cars, trains, buildings, animals, whatever. Okay, weather, life. Yeah, I have one. That would mean, if I did that, it means I wouldn't have one. Okay, so that wasn't very realistic. Plus, the Earth, the distance changes a little bit, believe it or not. Okay, we have tectonic shifts. Okay, we also have wobble. Yep, wobble. The Earth wobbles. Why might the Earth wobble? Well, it is spinning very fast, actually. Thousands of miles per hour. Ooh, I didn't use metric. Okay? What might be pulling on the Earth that causes it to go, ooh? Yeah.
The gravitational shift of planets getting close, but not dangerously close.
Very good. Very good. Jupiter has a huge pull on the Earth. If Jupiter didn't exist in our solar system, we would be consumed by the sun, believe it or not. Jupiter is very important for us. Without Jupiter, we would not be alive. Okay? The sun is pulling on us. If I were to place a replica of the sun here, it's so big that I'd have to place the Earth several classrooms over, and it would only be about the size of a pin. Okay? The sun is huge. It's absolutely massive. Every planet in the solar system can fit inside the sun with lots of room to spare. Okay, so the sun is huge. It pulls on us. It causes us to wobble a little bit. So that was not a very good way of defining the distance between 2 points, which is length. Okay, the distance between 2 points, the SI unit for that is the meter. Okay, so it is now defined as the distance light travels in so much time. In the distance light travels in 299,792,458th of a second. So notice, we need to define a second before we can define a meter. If we didn't know what a second was, we could never define a meter. Wouldn't be possible to. So sometimes our definitions really are very, very important. Okay, temperature. Temperature is interesting. Temperature, okay, is totally made up. Okay, totally. If I wanted to have a temperature scale called the Bornheimer, okay, and I could set it however I want. I could set 0 as room temperature right now. And I could say, okay, every time it goes up a little bit, we'll call that 1. Temperature is totally made up. It was these Celsius, Kelvin, Fahrenheit, these are guys that decided that they were going to make up a temperature scale. And it was just so popular that it got named after him. Okay, Lord Kelvin came up with the Kelvin scale. All right. They're defined on different things. Some are defined using water, some are defined using energy. It just depends. Okay, and we'll talk about different units of temperature. Kelvin is the one that we use the most. We do not use the word degrees with it because there is no degrees Kelvin. It's just Kelvin. Okay, and 0 Kelvin is based on energy, would be something that has absolutely no energy. Believe it or not, we've never reached 0 Kelvin. Gotten very close. But if something was at 0 Kelvin, it would mean that it absolutely has no energy at all. And there's nothing that doesn't have energy. Even this desk has lots of energy. If we were to zoom in on this desk, we would see that it's wiggling. Yep, it's wiggling. Check it out. Vibes. Be careful. Okay, so the measure of the, what do you think is temperature? These are all really good responses, guys. It's the measure of the energy of a substance. It's actually kinetic energy. There's a difference between normal energy and kinetic energy. Kinetic, kinestatics, how many of you have done like plyometric workouts? Anyone ever done a plyometric workout? Okay, these kinds of terms mean kinematic, kinesthetic, plyometrics, part of the same family. It means movement. So what we're talking about is energy that causes things to move. Right now, I have lots of kinetic energy, probably due to the coffee that I drank this morning. Okay, I'm moving around the room a lot. I move a lot. That means I have lots of kinetic energy. Anything that moves has kinetic energy. What we're actually measuring with temperature is the movement of the atoms of an object. Sometimes something has low energy. This desk doesn't have a whole lot of energy. It is moving at very, very small levels. If it had lots of kinetic energy, it'd be moving around on the floor. Okay? We're actually measuring the kinetic energy of a substance. By the way, this class, great input today. The third hour, it's like pulling teeth. Okay, mass. Okay, the measure of the matter in an object. Everything that we know in this room, for the most part, has got matter in it. Okay, it's physical stuff. And the only time I like to really use the word stuff is when we're talking about mass, matter. The SI unit is the kilogram. And believe it or not, there's literally a piece of metal sitting in France that is the definition of a kilogram. Yep, really high tech. Okay, sitting there on a pedestal. Okay, that's what a kilogram is. Everything that we define a kilogram by has to be compared against that block of metal in France. Okay, so that's how that works. Okay, which weighs more, a ton of feathers, a ton of lead? The same, yeah, it's totally like the old cliche. But yeah, the whole idea is that how much something weighs or whatever is arbitrary. What determines a object's weight? It's gravitational pull. So would my weight change off Earth? Absolutely it would. Okay, would I weigh more or less on the moon? I'd weigh less because the moon is smaller. Would I weigh more or less on Jupiter? Yeah, I weigh pretty heavy. I'm pretty heavy on Jupiter. I'm like 400 pounds or 500 pounds. Yeah, and I would be kind of squishy. I'd be like a squat. If I was on the sun, I'd weigh about 1,100 pounds. And that's when I'd really have to seek out Weight Watchers. Okay. But would I be any larger? No. As a matter of fact, if I was on the sun, I'd be more dense. It would kind of suck me in. Okay. So an object's size is not a very good representation of its weight or its mass. So we have to kind of get that out of our head. All right. This desk has mass, but a similar sized desk could weigh a lot less. Depends on what's inside it, how much matter is inside the desk itself. Okay. So this idea of mass versus weight is very important. We have to make sure we're using the right terms. All right. The measure of the amount of matter in an object is called mass. It does not change from place to place, and we measure it using the kilogram, not the gram. Okay, we use the kilogram because there are so many objects that are larger. The Earth is close to times 10 to the 24th kilograms in weight. We can actually weigh the Earth. Okay, we can find its mass. Okay, it's 10 to the 24th. That's a pretty big number. All right, the measure of the gravitational force between objects would be weight, and that changes. Okay? If, for instance, if you're in free fall, you might be weightless. You would actually weigh 0 pounds. Yeah.
I was at like one of my golf teachers.
Sure.
He held up like a golf ball and then a tee, and then he dropped it, and they like hit the ground at the same time.
Yep.
And I guess we kind of thought it was gonna be the ball that was gonna hit.
Because it weighs more, right?
Yeah.
That's what you thought?
But why is it that they both go at the same time?
They both drop at it's a good question. Next, I don't want to get ahead of me. Third unit, we'll talk about that. We'll experiment with it. And I might even, if I can, get on the roof and drop some things. Everything drops at the same rate. If I were to drop you in a golf ball at the same time, I went not from very high, don't worry. You'd hit the ground at the same time. It's one of those really cool quirks of nature, and we'll talk about it. But it does deal with this. Okay, it does deal with this idea. When objects fall, it's not dependent upon mass. It's not dependent upon weight. So it's kind of an interesting idea. Hold on to that question. Does anyone else have any input at this point? Yeah.
Well, if Earth is in space, shouldn't it weigh anything at all?
It does weigh because there's other objects with gravity that are affecting the Earth. Yeah.
When back in elementary school, one of my teachers tried to find the difference between mass and weight. I was asking someone what their favorite color is and them answering spaghetti.
Wow, that's really effective. Not sure where that was going. I'll have to talk to that teacher. The quantity of an object is the amount of substance one has. Amount being, we actually count them out. So if I have a baker's dozen, how many donuts do I have? 13. If I have a regular dozen, I have 12. Yeah. Okay? We use the mole to measure quantity. Now, we're not going to get heavy into the mole here. However, to give you an idea of how big a mole is and why we use it, let's talk about it. The mole of what do you think would spread over the surface of the Earth and produce a layer 50 miles thick? Whole surface of the Earth. What do you think? What could it be? If we had a mole of this, 6.02 times 10 to the 23rd of this object, what do you think? What object are we talking about?
Anything.
Well, not anything, because size matters in this particular scenario. What's that? What do we think? Say what? Okay, gold. If we're talking a gold bar, we got to go smaller. It's a smaller object. Pencils, smaller, larger than pencil lead. It's a little spherical object. A marble. If I had 1 mole of marbles, 6.02 times 10 to the 23rd, if I had just 1 mole of them, just one, it would cover the surface of the Earth 50 miles thick. To give you an idea of just how big that is, the tallest skyscrapers in the world are half a mile. And they're in Dubai. Half a mile, just over. It's like 2,700 feet or something like that. And it's new in the last couple of years. Okay, so we're talking the biggest man-made structures, half a mile. 1 mole of marbles, 50 miles. We're talking like crazy numbers. All right. If you had 1 mole of grains of sand, it would cover the surface of the United States 3 inches deep. 1 mole. Your average beach doesn't even have a mole of sand. Okay? If you had a mole of dollars, you could be spent at a rate of $1 billion a day for 1 trillion years, and you still wouldn't spend all of them. So a mole is huge. Why do we use it? What is the purpose? What do you think? What is the purpose of a mole? Sort of. Let's go really, really small the other direction. What do you think? Really, really small. We're going to not go planets. We're going to go the other direction. Tiny, hydrogen, helium.
Oh, okay, yeah, like atoms.
Atoms. Absolutely. Atoms. 1 mole of air. It's about yay big. Okay? Now, if a mole of marbles covers the surface of the Earth 50 miles thick, and the mole of air is this big, gives you an idea of how much smaller an atom is than a marble. Okay? That's why we have to use something like the mole, because we can work with reasonable numbers. Okay, in chemistry, and where we're looking at subatomic particles. Okay, that's the mole. Let's talk scientific notation. How many of you are familiar with it? Great. Scientific notation. I'm not going to go through every slide here. Basically, it's the method of expressing numbers as powers of 10. Numbers as powers of 10. It is really beneficial for us in a number of different ways. I'll go through these two examples. Okay, imagine for a moment that we have this first example, 2.03 times 10 squared. Okay, it's supposed to be 10 squared, not 102. If I want to turn it into a decimal, okay, I basically have to break it out of scientific notation. This is scientific notation for a couple of different reasons. First, I have only one number to the left of the decimal. If I had two, it would not be scientific notation, only one. Second, I have a times 10 here. Okay, this is an expression of the metric system. So times 10 is important. Even if it's times 10 to the 0, anything raised to a 0 power is what? 1. Very good. So even if it's 10 to the 0, it's still in scientific notation. If I want to break it out of scientific notation, I would just go 2.03 and break this down. This would actually be 100. Multiply it through, and the real answer is 203. Now, this first part here, 2.03, originally looks smaller than what our real number is. If that's the case, your exponent will always be positive. Okay? Because you're going to try to make this number, you're trying to make this number, by multiplying it by this, become really big. However, in our other scenario, 0.0678, we start with a small number. When I say large and small, I'm talking about basically anything greater or less than 1. So this is a small number. And if I want to turn it into scientific notation, I need to move the decimal how many places? 2. Which direction? In the right direction. And I'm not talking like correct, literally right. So we're going to go right 2 spots, and it's going to be 6.78. Am I done? Nope. What do I have to do? Times 10 to the negative 2. Times 10 to the negative 2. Now notice that's different than this one. I originally started with a small number. This actually looks bigger than what I started with. So in order to make it small, I compensate with the 10 to the negative 2, which is 0.01, basically. Okay? So this is going to be negative because my number actually got bigger from going from here to here. Or it looks bigger. It's not actually bigger. They're the same. So shifting the decimal, okay, is all about scientific notation. Some of you think this is just boring. And yeah, it basically is at this point. However, when you've mastered scientific notation, it really makes your life a lot easier. Okay, for a couple of different reasons. If we're working with the mass of the Earth, which we will a lot, or the mass of the sun, okay, we're talking about a number that has 24 zeros after it. Could you imagine writing 24 zeros every time you wanted to use that number? Wow, what a waste of time. Okay? We use scientific notation because it's actually shorter when we're working with large and small numbers to write it in scientific notation. It takes less time than it does to actually write it out longhand. It also is much easier to multiply and divide in scientific notation. We're going to talk through that as well. Okay? Advantages, it's basically large or small numbers. Here's a couple of tables that might help you if you're really confused about the idea. They're in your notes. Okay, to express a number, here's an example I worked through. The blank is left. Okay, the blank is left. You want only one digit to the left of the decimal. Okay, if you're going to multiply 2 digits expressed in scientific notation, if we multiply them, we multiply the first digits, and then we worry about the exponents. One of the things that you could really do you could, if you have a graphing calculator, is just write it all out and multiply the whole thing. That's fine. But actually, I can do problems faster on the board than I can on a graphing calculator if I use these methods most of the time. I can usually work through a problem faster than you can do it on a graphing calculator. Okay, and here's kind of how it works. Let's say for a moment that I have 2.0 times 10 squared times 1.0 times 10 to the third. Okay? To give you an idea of what these numbers really are, this is 200, this is 1,000. Okay? I'm working with simple numbers for the sake of a demonstration here. When I multiply these, if I use the rules here, I take only the first parts and I multiply them. 2 times 1 is? Very good. 2.0. Then I just add the exponents. How can I do that?
Um,
Properties of exponents, which is
if you're trying to multiply two exponents that have the same base, you're going to
the same base. Beautiful. Think about that. The metric system in its glory said, hey, let's just make the base 10 all the time. So we don't have to mess with the 10. We can just add the exponents. Bam, 10. Done. Times to raise to the what power? Fifth. Woo! Crazy. Yeah, crazy. All right. Now let's say we're going to divide them. Okay? How does that change our answer? 2 divided by 1 is? 2. Yeah, check it out. Okay, times 10 to the what this time? Negative 1. You're just going to take and you're going to subtract the exponents. Done. No fancy figuring out all the buttons on the calculator. Okay, trying to type it all out and hope that it turns out okay. You can just do it quickly on the board. Will all the numbers work out? No, they're not. But some can be done a lot faster this way than on a calculator. However, your graphic calculator is still a great resource, valuable in many ways. Okay, that's why I have one, and I still use it quite often. Okay, you're going to do a lot of calculations in this class. If you have programmed stuff in your calculator, that's really good too. We can talk through some of that later. Okay, so we talked through multiplication, division. Make sure that if your number, let's say that this was a 6, and this was multiplication. If 2 times 6 would be 12, this is not scientific notation. We have to move that decimal over 1. And in doing so, we have to compensate the exponent. Okay, so if I'm taking a number that is 12, okay, and this is sometimes what I do, and I want to turn it into 1.2, it's really going to be 1.2 times 10 to the first. If I substitute that back in as 1.2 times 10 to the first times 10 to the fifth, I can just add the exponents again. And it becomes 1.2 times 10 to the sixth. You have to make sure that if you end up with a number that has a decimal here, or even here, or so on and so forth, you turn it back into scientific notation. 1 digit to the left of the decimal. That's it. Okay? So you might have to compensate a little bit. If you have homework that'll help you practice this. And if you have questions, you let me know. Okay? All right, prefixes. Oh man, these are great. These are great. Why are prefixes so great? And they're not suffixes. What's the difference? Pre, like pre-game. Huh? Before. Yeah, they come before something. Ooh, we're on the right track. Okay, it doesn't mean before fixing something. We're not fixing anything here. What is it exactly? Does anyone know? Give me an example of a prefix. Kilo. Yeah. Okay, kilo. It means 1,000. It's literally a word, letters, that represent a number. Okay, so centi, like a centimeter, literally means 1/100th. Kilo means 1,000. Okay, mega means 1,000,000. Nano means it's like 1/100000th. Yeah, it's very, very small. Okay, nano. So when we're using prefixes, sometimes instead of writing something out in scientific notation, we can replace it with a prefix. Example. Let's say, we can actually use this 6.0 times 10 to the third. Let's say that this was in meters. I can replace the whole 10 times 10 to the negative third with a prefix and just tag it onto the unit. So this really becomes 6.0 kilometers. That's the power of a prefix. You're taking out this multiplier and you're replacing it with a known prefix, letter, that represents a number. Okay, so what this means is 6,000 meters. Instead of 6 times 10 to the third, which is 6,000 normal meters. That's what a prefix does for us. It becomes very useful when we're working in, there's certain numbers. Kilograms, for instance. What is 1 kilogram? How many grams? It's 1,000. It would really be 1 times 10 to the third grams. So 1 kilogram is 1,000 grams. Okay? When you have positive exponents, it's pretty easy. Okay? However, when you get into the negative exponents, you have to start thinking fractions, like 1/10, 1/100th, 1,000th. Okay? So, for instance, we might talk about a millimeter. Okay? 1 millimeter would be 1 times 10 to the negative third, or it literally is 1,000th, 1 over 1,000, makes it very small, and a millimeter is very small. Okay, so prefixes are very important for us. You are required to know some. Okay, this is a chart I gave you. It's kind of small. You can find basically a prefix table. You just search prefix table and you will get over 1 billion hits on Google. I mean, it's just so common, it's ridiculous. Yeah.
What was the blank for the chart?
Oh, thank you. If I skip one. We use prefixes as a shorthand way. Basically, it allows us to quickly express a number without having to write out it in scientific notation. Thank you very much. Courtney, right? Thank you. There's the prefix table. You have this big block of meh on your thing, and that's because it showed up as like solid yellow. You are basically have to know terra to femto. You just write that down, terra to femto. You can look it up online, get yourself a nice table, okay? That's it for today. We made it through everything. Your homework is on your Unit 1 outline. If you have questions, you email me. Otherwise, have a great day, folks.